remember you have an extra week for the problem set, and we'll have a discussion about it tomorrow. All right, so we're talking about the very important topic of multipole expansion, particularly in electrostatics right now. And the problem is that we want to find the electrostatic potential at a distance that's far away compared to the size of the charge distribution, okay? And in that limit, we can write the electrostatic potential in a power series in 1 over r, the distance from the origin to the point of observation, which is far compared to the size of the distribution. And that has a general form that's written here, okay? So we have this power series where the electrostatic potential, which has this exact form, assuming no other charges, all the charges in the problem, so this is the Green's function, has this form where we have a 1 over r term, and then a 1 over r squared term, 1 over r cubed term, et cetera, et cetera. And when r goes to infinity, the lowest non-vanishing term dominates, okay? So these terms are characterized by the multipole moments, which are characteristics of the charge distribution relative to the point of origin, okay? And the first is the monopole, which represents the net charge of the distribution. So if the charge has some net, if the distribution has some net charge Q net, then far away it looks like a point charge with at the origin with charge Q net, and the potential falls off like 1 bar. So this is the potential of a point charge. So if all else fails, and you're looking very far away from a charge distribution, and you can't see any details about its shape or its size, it looks like a point at the origin. And it just looks like the potential of a point charge, okay? But then there are correction terms, and those correction terms could dominate if the situation were, for example, that we had a neutral distribution with an equal amount of positive and negative charge. Then the first non-vanishing term would be this one, which would fall off like 1 over r squared, and it's characterized by the first moment, which is the dipole moment, which is a vector, okay? And then the next term that falls off like 1 over r cubed, that falls off like 1 over r cubed, is the quadrupole moment, and it's a tensor with, in principle, 9 components. Okay, so the components of the tensor are as given, and these are the sort of Cartesian moments. Meaning they're the components in Cartesian coordinates, okay? As opposed to the spherical moments, which we'll talk about a little bit today, okay? Yeah.
So on multiple expansion, why does it like the 10 beyond the quadruple moments? Why do they not matter?
I'm sorry, can you repeat the question?
I mean the 10s beyond the quadruple moments.
Yeah, they will matter, but typically it's rare that we have a distribution where the monopole, dipole, and quadrupole all vanish. We could definitely create a distribution like that. For example, if I had things on the corners of a cube, the 8 corners of a cube that were equal and opposite, plus and minus, the quadrupoles would cancel, and we'd have an octupole. It's always 2 to the nth pole, because you have to put another 2 charges above them. So each time the pole is 2 to the nth. So we could have something which is dominated by the one of our fourth type, which would be an octupole. But that's not, you know, at that point we just talk about it in generality. We typically just focus on the properties of the dipole and the quadrupole, and then anything beyond that is a kind of more general object that we'll discuss more today. All right? Thank you for the question. All right, so I wanted to just mention one thing that's going to be important as we continue is so, you know, what we said here, this is about the net charge. This is about the sort of distance between positive and negative charges. So if we have a separation of positive and negative charges in our system, then the electric dipole points along the direction of the separation with a magnitude that depends on the difference between those positive and negative charges. Okay? And the quadrupole is saying something about the non-spherical symmetry of the distribution. As we've discussed, we emphasized last lecture, if I had a situation where I had a spherically symmetric charge distribution, which is spherically symmetric around the origin, well then it only has a monopole moment, no matter how spread from the origin it is, because we know that from Gauss's law, right, that we can write the electric field as the electric field that is falling off like 1 over r squared, and therefore the potential falls off like 1 over r if we have a spherically symmetric distribution. So if we have a spherically symmetric distribution, it's monopole, okay? So, but if we had an oblong distribution, it would have a quadrupole, okay? Like you're studying in your homework if you looked at that. Yeah, okay. Yes?
So like this multiple expansion is an approximation, right?
Could you say again?
This multiple expansion is an approximation, right?
It's a Taylor series expansion.
So
physics is about approximations, okay? So physics, we never do anything exactly. The art of physics is the art of approximations, but approximation means, it feels good to me, that's good enough. No, what an approximation is, I know how good this is and what the corrections are. It's what we call a controlled approximation. So we can say how good this approximation is and what we're leaving out. It is an approximation, but it's an excellent approximation when the small parameter, as you know from the rigorous theory of Taylor series, you can ask how well the function, what's the difference between the exact function and a finite power series that approximates that function, and what the correction terms are. Okay? So an approximation doesn't mean it's not worth anything. Physics is approximations. We don't know anything exactly in this world. Nothing. And now everything. What do we know? Everything we're doing is an approximation to life. We do the best we can. And what do we know about string theory? You know, it's not done, so don't take the thing. It's approximation. Man, it's not good. Approximation is what it's all about. All right, so, what was I going to say? Oh, yeah. So we talked about a non-spherically symmetric distribution. I want to talk about the specific case of azimuthal symmetry. Or what we sometimes call cylindrical symmetry. So this is the situation where the charge distribution has an axis whereby, as a function of the azimuthal angle, which we typically call phi, the charge distribution is the same, okay? So for example, you know, I might have, as we have in the homework, a spheroid of charge, which we call this the z-axis, where the charge distribution depends on the distance from the origin and theta, but doesn't depend on phi, okay? So R is only a function of theta and phi. R and theta, but independent of phi. It's the same no matter what phi is.
Phi is the one that just from 0 to pi, or sorry.
That's right. So theta goes from 0 to pi, and phi goes from 0 to 2 pi, right? Or, you know, I have 2 point charges on the z-axis. That also has azimuthal symmetry. It depends on R and theta, but it doesn't depend on phi. It's only non-zero at theta equals 0, but that's also azimuthal dependence. Okay, let's take a look at that case. So let's look at, for example, the dipole. These are the components of the dipole vector, okay? What can we say about them, okay? So we're integrating over all space. In this case, if this is independent of phi, this volume element is, as Benny said, we integrate over phi, so it's 2 pi r squared dr d cos theta. That's always the way to write the element of spherical order. Instead of sine theta d theta, it's d cosine theta, where cosine theta goes from -1 to 1. It's the much better way to always write the Jacobian. There's a minus sign, but you just have to flip the order of the. Okay, so let's say we had that, okay? And what about x? Well, okay, remember that these are the components, you know, x1 is x, which is r sine theta cos phi. x2 is y, which is r sine theta sine phi. And x3 is z, which is r sine theta, cos theta, right? So, given that fact, what can we say about the components of this if the charge density has azimuthal symmetry? For example, what is P1, which is Px in this case? If I plug in this here,
R sine theta.
I have to integrate over phi. I'm sorry, there's a this I made a boo-boo. I have this depends on phi, so I can't put a 2 pi there. I have to integrate over phi. Write that from the record. I'm looking at you, YouTube. All right. Okay, now what is this?
Is it 0?
It's 0 because I'm integrating over phi, and x is, when I integrate x over phi, it's 0. And what about py?
Same thing.
Same thing. What about pz? Well, that's not. So pz, in this case, now this doesn't depend on that, so I can write this as integral dq x r cos theta times the p of r and theta. Okay? So when I have azimuthal symmetry, only the z component of the dipole is non-zero. Okay? I note that this, I will write this, this is actually proportional to P1 cosine theta, where P1 is of mu is the Legendre polynomial. Legendre
mentioned Dre.
Yeah, and that's one of those Wordle in the other language kind of things. All right, so, that's kind of interesting. What about, let's look now at the components of the quadrupole moment tensor, okay? And let's look first at the case where I doesn't equal j. Okay, so that is equal to, in that case, when I doesn't equal j, these components are 0, because that is only components on the diagonal. And so we have the integral over all space, xi, xj, times rho, which is only a function of r and theta. Okay? So what can you tell me about those elements given this, if I look at any of these combinations where they're not the same? Either, let's look at x1, x3, or x2, x3, or x1, x2. Any one of those. And I plug them in, and I integrate them over phi. What do I get?
Still 0.
0, right? Because one of them is going to be cosine theta, phi, that's 0. One of them is going to be sine phi, that's 0. Then one's going to be sine times cosine, which is proportional to sine 2 phi, which is also 0 when you integrate. So all the off-diagonal elements, if I have azimuthal symmetry, are 0. And so the only non-zero components are on the diagonal, okay? However, we also know that this tensor is traceless. It's symmetric and traceless. It's irreducible. We'll come back to remind ourselves more about that soon. And so what that tells me is that the trace, which is the sum of the diagonal elements, which is qxx plus qyy plus qzz, these are all equal to 0. The sum of those is 0. That's the sum of the diagonal elements of the, who's the was it? Yeah. Of the matrix.
But I thought we were examining only I is not equal to j.
No, that was the second. Which I wanted to, first, we know something about the off-diagonal elements are all 0. Now I want to say something about the diagonal elements. Now, the diagonal elements are constrained in this way, okay? But there's more. If it has azimuthal symmetry, we can't tell the difference between x and y. No one knows. Anywhere in the equator, oh, I'm getting dizzy, is the same, right? So what's the difference between x and y? Nothing. We can't tell. There is no x, there is no y. Everything in the equator is the same. So that means that there's no difference. This must be equal, because who says x and who says what's y? So this is equal to twice 2qxx plus qzz, which is 0, which means that qxx is minus a half qzz, if I have azimuthal symmetry. This is not generally true. This is, we're looking at this specific case, okay? And given that fact, what this says is that if I have azimuthal symmetry, there's only one number that determines the whole tensor, and that's qzz. Because all the off-diagonal elements are 0, and both qxx and qyy are minus a half qzz. So when we have azimuthal symmetry, the tensor is qzz minus a half, 1. So this one number is called the quadrupole moment. So in your homework, in the Jackson problem, he talks about the quadrupole moment, which is this one number, because it's the one number that defines the whole tensor when you have azimuthal symmetry. But I just looked this up because Omar was asking me in the problems, and I forgot about this. In nuclear physics, there's a little weirdo thing where people call the quadrupole moment Q as QZZ divided by the charge of the electron. It's called the quadrupole in nuclear physics. So in the Jackson problem, that's what so this thing has the units then of length squared, right? Because the quadrupole tensor is charge times length squared, okay? Yes?
And then the quadrupole moment we said last time has 5
General.
degrees of freedom.
In this case, it only has one,
Yeah.
because it's the only one that's non-vanishing.
Yeah.
But the most general one has 5. They're related to the 5 different components of spherical harmonics when L equals 2, which we'll discuss in a moment.
Where do we get that the trace is 0?
What is the trace of this?
Right.
This is 3, this is r squared, voila. So this in fact is traceless. It's also symmetric. If I change, write it in any order, it's a symmetric traceless tensor, it's irreducible, it has 5 independent components. Very good. Sorry I screwed up. I should be on this board first, but you know, such is life. All right, so let's now look at this one and only one independent component of the quadrupole moment. So QZZ is equal to the integral over all space 3 z squared minus r squared integrated over the charge density. Okay, so is everyone clear? I'm looking at that particular component of the tensor. And we just said that z is r cosine theta, so this is equal to 3 r squared cosine squared theta minus r squared, or squared.
How many integrals is this? 2?
Integral over price. Sorry. Yeah, integrated over all space. Don't swear. All right. Anyone recognize that function?
Polynomial.
It's the Legendre polynomial P2. It's actually tristat. It's proportion. I mean, the Legendre polynomial of cosine theta. Right. P2 of mu is 1/2 3 mu squared minus 1. So this is a pattern that we're going to explain. It's not for nothing. This is also r to the power 1, and this is r to the power 2. This z component, this non-vanishing component of the moment, for this kind of azimuthal symmetry has this form, and they're related to the spherical components of the moment that we're going to discuss soon. Okay? Now, I want to say one last thing about this. Given this moment, let us write what the potential is. Okay? So when we have azimuthal symmetry, I can look at the quadrupole potential for azimuthal symmetry. Okay, so I'm going to write, so the quadrupole part of the potential, I'll just rewrite it again, 1/2 r hat dot q over r to the third, okay? And now I'm going to multiply top and bottom by r and write this as x dot q dot x r to the fifth. Just multiplying top and bottom by r, and the position vector is r times the unit vector, okay? which is equal to, in general, xi, xj, qij over r to the fifth, summed over I, summed over j. But when we have azimuthal symmetry, only the diagonal terms are non-zero. So this is then equal to x squared q xx plus y squared qzz plus z squared, oh sorry, qyy zz over r to the fifth.
QXX plus QYY.
Are we correct? Yes. But this and this are equal to minus a half of qzz. So this is equal to qzz over 2r to the fifth, and then I have z squared minus x squared plus y squared over 2. As I plugged in qxx and qyy were equal to minus a half qzz, and then I factored out the qzz. Okay? But x squared plus y squared is r squared minus z squared. So all of this together is equal to, I have 1 plus a half, which is 3 halves z squared minus r squared over 2. That's an r, not a m. Right? So putting that all together, and now I can factor out an r squared. This is equal to r squared cos squared theta, as we did before. What I find is that the quadrupole, the potential associated with a quadrupole when I have azimuthal symmetry is equal to qzz over 3 cos squared theta minus 1 over 2, which is the Legendre polynomial. So the same thing well, I guess there was this other factor of 2 over here. Those factors of 2 are annoying, but they're there. So we're going to come back to this, but the thing I want you to take away from this is the following. We obtained the quadrupole moment, that's to say the one thing that defined the whole quadrupole tensor, by taking the charge distribution and integrating over all space, but as far as the angular dependence went, we projected the distribution over, we projected it by multiplying it by a Legendre polynomial, in this case P2 of cosine theta, and integrating over that, and we got the moment. And then, moreover, given that moment, the potential associated with that has an angular dependence, which is the same polynomial. That's related, as we will see in a moment, to the whole decomposition in terms of orthogonal polynomials on the sphere. Yeah?
This is still lecture 6?
Still lecture 6. We'll be in lecture 6 all day today. All right, good. Oh boy, we got lots to do. All right. So now I want to come to the question of the general Cartesian expansion. So we started this last time. I'm gonna now go a little fast and then we'll catch up. So we want to look at a Taylor series expansion of our Green's function when the distance is far of observation compared to the points in the charge. And I said, oh, I can write this like this because I'm fancy. Okay, and this is 1 over r. And then I just write the Taylor series expansion for the exponential and then, to the power L. And then I can write this out. So this is equal to xi prime the partial respect to xi summed over I. That's what that dot product is. And then I'm going to do that to power L, so I'm going to get L different terms. So I'm going to write that as a sum. Well, I'm going to use Einstein's summation convention because it's easier. I1, 2, there are L different guys of that, and then partial I1, partial I2, dot. So that's just this, L times, with L different dummy indices acting on 1 over L. Okay? And this is the contraction of 2 tensors. This tensor is just the outer product of x prime with itself L times, and these are its components. And I'll call that tensor P, or polynomial. And this is some other tensor which has components like that. Okay? And it's the contraction of those 2 tensors. So this is a very formal expression for this Taylor series expansion, but there's method to this madness. Okay? So let's just look at some of these tensors. So let's look at the first order tensor. Let's look at the case where I have the case where L equals 1, so I'll just have Ti acting on 1 over R, which is the partial respect to I for this guy 1 over R. Okay? Now, I've screwed this up so many times in class and in my notes. I want to show you how to do this easily, because I don't know what was going on in my mind. We use the rules of calculus, and this is equal to, I take the derivative, remember this is a function of x1, x2, x3, so I use a chain rule, and I get 1 over r squared times the partial with respect to I of r. Does someone have a question?
Yeah, I just want to make sure that the T tensor doesn't include the 1 over r.
It does.
It does.
It does. It's this whole thing.
Okay.
Everything that this, and so this is the case where I just look at the 1 term in this, where L equals 1, then that's the first tensor over
Should
here.
there be a negative?
Yeah, there should.
Okay.
Yeah.
Okay.
Okay, so now the question is, what is that?
I is either X, Y, or Z? Or
It's any, yeah, it's one of those, right? So this is, I can think about this is, so, yeah, there's lots of different ways to think about that. But, you know, R is the square root of x squared plus y squared plus z squared, which is that. So I have to take the derivative with respect to that. And when I do that, what do I get? Xi over R, right? Okay, so that's what that is. Okay. All right. So if I were to take, for example, the second order case of that, what do I get? Oh, well, let's just look at that particular term in our,
Are you missing a one?
I'm missing what?
A 1/2 is. Alright, guys.
No, I have two terms, right? Because I do it twice. So the half is going to cancel. Think about it more easily, maybe this. What is partial respect to x of x squared plus y squared plus z squared, right? There's a 2 that comes down. So if I did this, that factor of 2 cancels. Okay? Very good. So what is, let's look at this. This is Tij. So that's that guy. So I can do the partial respect to I first. I did that. So I get minus partial respect to j xj over r cubed. Right? How do I do that?
Now you have 2J.
I do, because I screwed up. That should be I. So I did this. Yep.
So you take the xi out, so this
No, it does. I mean, it's not I and j. This is the partial. So, question: what is partial xj of xi? No.
It'll be 0 if I and J aren't. the same.
Right? But if they are, it's a Conover delta.
I see.
Okay, good, excellent. So this is equal to minus delta ij r cubed plus the partial respect to j of 1 over r cubed. Which is what? Well, I use the old chain rule again. And that's then equal to minus 3 over r to the 4th partial j of r. Right? Because that's how I take that derivative in calculus 1. Right? And what's that? Well, it's this, but now we're j instead of I, right? So, you know, this is, it,
Yeah, xj over r.
how did I get the units wrong here?
I think you may have missed an xi earlier. When,
Oh, yeah. There's an xi here. Thank you. I lost the xi when I did the product rule. Right. Very good. So does that have the right units? It should be 1 over r to the 3rd, which it is, right? Because I took 2 derivatives. This is 1 over r. I took 2 derivatives, so it's all good. Okay? So what do I get here? I get, this is equal to 3xi xj minus r squared over r to the 5th. Oh, that looks familiar. Yeah.
What's the derivative right by your head off to the right? There's 2 stacked bells. What's the, at the end of the line? Up one line? Yeah, and over to the right. There's, the right.
That right.
Yeah. Yeah, so what is the derivative with respect to? We have del over del.
It's del J. It's del over
Del
J.
J, okay.
Sorry. Does that make sense? It's the partial derivative thing. All right, so what we see, let's just look at these first three terms in the power series. What we have is 1 over r x minus x prime is equal to, for L equals 0, well, that's just 1 over r. When L equals 1, I got minus 1 times 1, I get minus xi times xi over r cubed. That's what I got. And then I get minus, here comes a plus, squared 2 xi prime xj prime times 3 xi xj minus r squared over r to the 5th plus dot dot dot. Okay. This is just what we had before, but in a tricky-dicky way with tensor notation. This is the Green's function. If I integrate this over the charge distribution on both sides, this first term is going to give me the dipole moment, right? This should be r to the 3rd, sorry, r to the 3rd, not r to the 5th. And then I get the quadrupole moment, etc., etc., etc. So we have a general form. In fact, the following is true. Ti1 dot Ti2 is symmetric with respect to exchange of any two indices. We see that by definition. I can change these two indices, and because it doesn't matter the order in which I do the partials, because this is a nice smooth function, it's the same. Moreover, if I trace over any two indices, so for example, I trace over I1 and I2, that's equal to that's what it means to trace. I've contracted over these two indices. Yeah.
Where is the third ID?
Can you say again?
Third ID. Tij equals to Tij equals to 0xi.
Oh yeah, delta ij. Excuse me. Absolutely. Yes. Thank you. Thank you. Yes. Okay. If I trace over those two indices, I sum over these two indices, what is this thing? It's del squared, which is 0. Doesn't matter which two indices I get, when I trace over those two indices, this thing traces to 0. And we saw that in this case, right? If I trace this over I and j, the second ranked part of this is 0. So what we have learned is that this tensor is symmetric and traceless when I trace over any two indices. Such a tensor is known as an irreducible tensor, which is closely related to the spherical harmonics, as we will see in a moment. Okay? When we have the irreducible tensor, because of that, my Green's function can be written in the following way. Oh, maybe before I do that, I should say the following thing in my notes here. Right, so generally, this tensor has the following form. -1 to the L, 2L minus 1 double factorial, God, x 1, x2, up to xl, the irreducible part of that to the power r to the 2l plus 1. So 2l minus 1 double factorial, or let's just say a double factorial is a times a minus 2 times a minus 4, dot, dot, dot. That's what double factorial means. In the same way that factorial is you subtract 1, double factorial means you subtract 2.
He's even more excited.
All right, let's just take a look at this. This I didn't prove because God knows I'm not going to do that on the board. But does this what we found for the case, say, L equals 1? Well, in L equals 1, that's easy. That's what we just had before. That's -1 x over xi over r cubed. Voila, that's what we got. What about for L equals 2? For L equals 2, what is xi, xj? What is the irreducible part of this tensor? That's what this means. Well, I take the tensor, which is already symmetric, and I subtract out its trace. This is the irreducible part of this tensor because it's traceless. It's already symmetric. Now, is that what we got before? Well, we had this factor of 3, so I have to multiply. What is 2L minus 1? L is 2. So this is 2 times 2 minus 1 is 3. 3 double factorial is 3. So 3 times that gives me 3 minus 1 is what we got. So it worked. At least we checked it. Yeah.
Could you speak more about what's in that bracket?
What this is?
Yeah.
What this means is I take this tensor, which is just the outer product of x with itself, and I subtract out all the traces.
I guess what I'm wondering is what is the difference between, like, what is in those dot dot dots, and what determines how many things are in between them?
This is just the Lth term in the power series.
L.
So we had a power series. Where did it go? Here it is. The power series started at 0. I have the 0th term, the 1st term. So L indexes which term in the power series, which moment I'm talking about. L equals 0 is the monopole term. So if I were to write this out explicitly, this is equal to 1 over r minus v minus xi partial I 1 over r plus a half xi xj partial I partial j 1 over r plus dot dot dot. That's what this is.
So then you have xi, xj, and xk as well?
That's the next term.
Yeah,
The
okay.
next term would be -1/3 factorial xi, xj, xk, partial I, partial j, partial k, 1/r.
And you have as many partials and as many x's as you do l's.
That's right.
Yeah.
L is the Lth term in the series.
Yes. Thank you for clarifying.
So this is the polynomial, this is the tensor, and this tensor is this. Okay, so with that said, what I have is the following. The Green's function is equal to, given this, over L factorial, because oh, I gotta have all those damn factorials. -1 to the L times 2 on minus 1, so that cancels that. I told you to buckle your seats. You forgot. This is tedious, but the end result, hopefully, will be worth it.
All in the general series solution.
Okay? So what we have done with a lot of machinations is we've taken the Green's function and we've written it into a sum of terms which factorizes the coordinates that depend on the charge, the primes, and the coordinates that depend on the position. And the way we factorized it in terms of polynomials of order L, and those are very special polynomials. Each one of these polynomials, depending on whether this is x, y, or z, represent the components of an irreducible tensor. And there are two L plus 1 independent components of a rank L irreducible tensor.
Which makes sense because we plug in L equals 2.
For L equals 2, 2 times 2 plus 1 is 5. Okay? When we had L equals 1, 2 times 1 plus 1 is 3. Those are the three independent components of the dipole. And then the octopole would have how many? 7. Okay, etc., etc. Now, I did this quick sleight of hand over here. This polynomial wasn't irreducible. But all of a sudden, Deutsch put a superscript. Why the hell was he allowed to do that? There was no superscript here. This guy, we showed was irreducible. Because when we traced it, but this wasn't. Why did I all of a sudden allow to do that? Because I'm contracting two tensors and it picks off only the irreducible piece, which we proved in problem set 1. Maybe we didn't understand how we were doing, but that's what we did. We showed that when you contract two tensors together, you pick off only the irreducible pieces. So I only need to look at the irreducible piece of that. Yeah.
Is that related to the fact that, like, because a lot of us took quantum last semester, and it was if if your one thing is irreducible and you rotate it, it will never leave that.
That's right.
irreducible
So
state.
that's exactly what we're about to talk about. So thank you for that. The term irreducible is related to something that's reducible. Okay? So what the hell is reducible and what's irreducible? Okay? So let's just do a little bit. Okay, so with that said, before I do that, let me just say, so now we have the following thing. We have that the potential, we have a power series expansion for this, which is equal to a sum over L, 1 over L factorial, QL I1 to IL, X I1, X I2, up to XL, the irreducible part of that, to the power R to 2L plus 1, where QL, with these L indices, is defined to be equal to 2L minus 1 double factorial, the integral over all x primes, the irreducible part of that polynomial, rho of x prime. This is the general Cartesian multipole expansion. What do we see here? The potential is expanded in terms that fall off with different powers. Notice, how does this thing depend? Let me just say something. This guy over here is equal to something which goes like R to the L and some function which depends on theta and phi. Because x, y, z are all proportional to L. I'm sorry, they're all proportional to R, and there are L terms of them. So it's proportional to R to the L, and then some function of theta and phi for all the different components.
That part is an L, not a row, right?
Where, how, why, this?
No, left.
L.
Down. Thank you, sir.
Is everyone clear on that? So this thing goes like R to the L, so this goes really like a function of theta over the power R to the L plus 1. Right? And so for the monopole, when L is 0, it goes like 1 over R. For the dipole, L plus 1 goes like R squared. For the quadrupole, L plus 1 is R cubed, etc., etc.
R, what is
Because
L from?
this cancels. I'm saying what's in the numerator is proportional to R to the L.
Oh, I see.
So what's really in the denominator is proportional to the R to the L plus 1. Because what's in the numerator is proportional to R to the L. Yes? We have one question for another 2 minutes.
That L brackets, that means L's rank irreducible.
The L irreducible part of that tensor, that's
It
my...
doesn't mean the exponent.
No, it doesn't. It means,
And in the definition of Q, we should
that's
have-
also, it's just saying, the definition of Q, this should be L. Absolutely, Mark, thank you.
Can we write this in terms of the general?
We will. We'll actually write them in terms of spherical harmonics very soon. The story of irreducible tensors is coming together, and it's coming together now. Okay, so this guy, we just said, is a polynomial in x, y, and z. Does any of these things be either x or y or z? Oh, I'm sorry, I missed your question, pardon me. Excuse me.
Just out of curiosity,
Yeah.
I just want to know, like, the concept of double factorial.
Yeah.
Is this something that is mathematically standardized, or something just generates for companies?
No, it is a mathematical generalization of the gamma function. Yeah. Okay. So this is a polynomial of order L in x, y, and z. Like the ones we saw before, 3z squared minus x squared plus y squared plus z squared. That was a second order polynomial. But it's also what we said is something which has an angular dependence. It has some dependence on theta and phi. It's kind of a complicated one, but one nonetheless that we saw the case where L equals 2, that theta dependence was related to the Legendre polynomial. It was related to P2 of cosine theta. It had a very particular angular dependence. And in particular, the following was true. So recall the definition of a tensor. So if I had a tensor that wasn't irreducible, let me call it W, I1, I2, up to IL, rank L. Then in a new reference frame, which is in a rotated frame, when we did either an active or passive transformation, we went to a new reference frame that was rotated. We can ask, what are the components of the tensor in the new frame? Okay? And by definition, the new components are related to the old components by the rotation matrix on each indice. So that's the definition of a rank L tensor. Okay? That's how, if its components transform this way under rotation, we call it a rank L tensor. A rank 1 tensor was a vector, right? So we have a vector. Then, what do we have? If we have a vector, then we say that the vector in the new frame is related to the vector in the components of the vector are related to the rotation matrix. Okay? So every one of these three components, x, y, and z, transform into one another. Okay? However, beyond rank 1, I can, if I have a tensor which is rank 2, we can rotate this tensor, and it looks like all 9 components transform into one another. But if I break this tensor up in the following way, which I can do. Well, let me have a different tensor. Okay. It's clear that the right-hand side of this equation equals the left-hand side of the equation. Because this cancels this, and this cancels that, and I get the same thing back. But this has one component, this has 3 independent components, this has 5 independent components, and when I rotate, this component only doesn't change. These guys transform into each other without affecting those guys. And these 5 guys transform into one another without affecting the others. And that is the notion of this tensor is reducible, whereas these tensors are irreducible. There's no way to further reduce them. They are irreducible. I can't reduce no further to make fewer components that transform into one another under rotation. Okay? Now that's intimately related to the theory of rotations, what we know from quantum mechanics as angular momentum, and from mathematical physics as this theory of spherical harmonics. And so let us connect those guys together. What this is saying in some sense is that this particular dependence on theta and phi is just the right way that these components don't transform into anything other than into themselves. Okay. So, I'm not going to prove this. The following is true. I can rewrite our friend the Green's function in the following way. Make sure I get the factors right. Yeah, I would have forgotten that. Because that's the way it works.
Jackson.
Because Jackson said so?
Well, no, because, I mean, otherwise, I mean, just because these are orthogonal functions in this way. So here, of course, R is greater than R prime. So, because I'm far away from the distribution. Okay. So this, if we look at this function, let me look at this in a slightly different way. Let's take out the for pi. I'm going to have the sum over L, sum over M goes from minus L to plus L. R prime Y L M star theta and phi. R L Y L M theta phi over R to the 2L plus 1. I just multiplied top and bottom by R to the L. Let's take a close look at this expression and let us compare it to this expression. Do they look similar? They're very similar.
What is a double sum?
Both of them are double sums because this guy has a sum over these indices. And in fact, there are how many independent indices? There are only 2L plus 1 terms that are non-zero. Let me just finish and I'll get your question. In this sum, right? How many terms are here? M goes from minus L to plus L. There are 2L plus 1 here. They're the same thing. They're not exactly the same thing because here what I had is some function of theta and phi, whereas here I have a very particular function of theta and phi, which are our friends that you know very well, the spherical harmonics. So the components of the multipole, which is obtained by multiplying the charge distribution by a particular polynomial in x and y and integrating, is very closely related to multiplying by this function of the coordinates. Something that goes like R to L, but the spherical harmonics. Okay? Yes, a question.
Did you absorb the factor of 1 over 2L plus 1 into something, or did you forget it?
1 over 2, no, I forgot it. I forgot it. Yep. It's in there, it's gotta be in there. It's in there. Yep. So, what we have is that the irreducible components of the tensor are really R to the L times something that looks like the spherical harmonics. They're not exactly that, and Benny was kind of clued in by there's complex numbers here. These guys are all real. These guys can be complex, right? They're Legendre, associated Legendres times e to the I m times phi. But these guys are just the real and imaginary parts, as we will see, of those guys. When I look at the case where I have, where they're real for m equals 0, they're exactly the same. Okay. So I just want to conclude today's lecture because we're going to need it with what, given this fact, I can write down the general expansion of the multiple expansion, but in spherical, coordinates rather than in Cartesian coordinates. Okay? So, what we finally have is the following thing. So what that means is that phi of x, which is the integral over the charge distribution times the Green's function, plugging in what's called the addition theorem, we get the following thing. The sum over L equals 0 to infinity, sum over M goes from minus L to L, 4 pi over 2L plus 1, QLM, YLM of theta and phi over R to the L plus 1, where QLM is defined as the integral over the charge distribution of R to the L, Y star, LM, theta and phi. Let's just take a quick look at this and then we'll conclude. This is the expression given in Jackson's text from the beginning. He didn't do all the Cartesian stuff. But you just won't understand where anything comes from if you just started there.
I thought you were doing this in Cartesian as well.
We did it in Cartesian.
Oh.
Now we're doing it in spherical. And they're related. They're related. The polynomials in x, y, and z are just R to the L times the YLMs, or the real imaginary parts thereof. These guys are known as the spherical multipole modes. For a given L, how many different M's are there? 2L plus 1. So there are 2L plus 1 components for a given L. L equals 1 is the monopole. I'm sorry. L equals 0 is the monopole. What is Y00? Yeah, it's a constant. So, and R to 0, so it's just the total charge, right? Because the 4 pi's would cancel, right? When L equals 1, well, those are Z, X plus IY, and X minus IY. Because, show why that's true. That's what those are the 3 components. When L equals 2, they're related to the second order Legendre polynomials, which we've already seen. The point here is that the Lth moment has 2L plus 1 components, and those 2L plus 1 components are they're linear combinations of the 2L plus 1 components of the irreducible tensor. They're one and the same expressed in Cartesian coordinates versus spherical coordinates. And so the way that I obtain this component of the moment is I take the charge distribution and I project it onto the direction associated with this YLM by multiplying it by Y star, right? That's how you do it in wave mechanics. You multiply it by the complex conjugate, and it projects it onto that sphere. And given that, the potential associated with that strength has an angular dependence, which is the same, just like we had with the Legendre polynomials. Yeah?
First question, is there E2 missing there?
Is something missing?
In the denominator for the R, the core of R, under the Y lane?
No, it's to L plus 1.
Okay.
I wrote it here. I can cancel one of those.
R,
Yeah, so it goes, I just wrote it that way because this form is this form.
corresponds to that, right?
You should think about that and then keep tapping the board until you look at this over and over again to put that in your brain that these things are the same thing. They're just linear combinations. Next question.
So like, for, hypothetically, for exam 6, are we supposed to have like, all the expressions of the widening, like there?
No, absolutely not. I promise you, there's no, everything you need to know I will give you. You will not need to memorize anything. Yeah. Except the binomial theorem. Yeah.
Violence are complex.
Yes.
But if I pick one L and write all the M's,
Yeah.
then I should get exactly that.
That's correct. And so let me give a quick example. Let's look at y1 plus or minus 1, y1, 0. Okay? This is equal to square root of 4 pi over 3. See, I remember this. It's crazy. But I can make it a problem. Cosine theta. This is equal to, and this one is the 8 pi, and this is 4 pi over 3 sine theta e to the plus or minus I phi. Okay? Let's look at r times this. Because that's what comes in to power 1. This is equal to r sine theta cos phi plus or minus I r sine theta sine phi, using that. Does anyone recognize that? What is r cosine theta? Z. What is r sine theta cosine phi? X. Y. So this is x plus I, y minus, and this is z. These are the three, this is how you should think about the spherical harmonics. They are components there that are related to polynomials in z and x plus or minus I, y. This is the same thing except it's the real and imaginary parts of that.
And both is equally as general as the other?
Totally, they're just the same thing, we just did it in two different ways. One way I pulled Jackson out of my something and just did it without deriving it, but it is the same thing. I just wanted to show this because we have to understand this both from the point of view of the Cartesian components. We never use these guys, we always use these guys. But they're related to one another. I've kept you long enough. My passion for this subject is overwhelming, and walking through there and to,
Yeah.